I have a small bulb here which is producing shadows on this optic screen of a square of length 1 centimetre, mounted, placed at the centre of this piece of plastic. If I now introduce a second screen which has got four squares, and align the position this so that it is trying to keep it square, with that the four squares are within the shadow. The shadow of the four squares is within the shadow of the one square. And then I have this one, which is 9 squares, and I attempt to do the same, keeping the shadow of the 9 squares coincident with the shadow of the 1 and 4 squares. At this point, we'll manage to make a note of the distance between them, and you can see that the distance between each of these is 1, although the light going through here is 1 unit. The light coming through here is 1 unit spread across 4 units, and the light coming through here is 1 unit spread across 9 units, thus showing the inverse square law. So I'm going to start this by looking at an AC signal. This is a 2-volt AC signal, and what I'm wanting to do is to do a bit of mathematical analysis of this. So what I'm going to do is now use this maths channel to add a value which is the A channel squared, and you'll notice that this would be more representative of, say, the heat given out by a resistor or whatever. And I think this is a good approximation to the intensity thing. So if you think of heat and light, and the amount of light giving out is proportional to the square of the amplitude. You see you had the amplitude on the blue trace, but this black trace, although it's the scales are different, see it's between the values of 10 and 0, whereas the actual trace on the blue scale is just short of 3 and 0 and minus 3. This is always positive. The black trace is always positive, and you can see it crosses where there is a 0. So from your maths you would understand that.